In this video, we will look at how to take antiderivatives of functions involving the form for the natural log. Okay, so in the previous section, we learned how to take derivatives involving natural log functions, and so now we just have to be able to take an integrand and fit it into the pattern of a natural log derivative. So in other words, what we want to do is we want to get our integrals to be in one of these two forms. So the integral of 1 over x or the integral of 1 over u. And once we have it into that pattern, we know that those answers will just, going backwards, so undoing the differentiation, we know that those answers will just be the natural log of the absolute value of x or the natural log of the absolute value of u. Okay, and we're going to talk a little bit more in class about why we need the absolute value symbol, but for right now, let's just, you guys know what the domain is of natural log, so we'll just, we'll go with the vague answer of the domain of natural log, and we'll discuss that more in class when we are face-to-face. Okay, so let's look at some of these examples. Again, for right now, on these basic examples, all you want to do is use the strategy of getting the integrand into one of the two forms, so 1 over x or 1 over u. Okay, so for example 1, we have an integral of 2 over x plus 2. And obviously this is not in the form of 1 over x, but this could be in the form of 1 over u. So if we let u be the x plus 2, using u substitution, du, remember that's just going to be the derivative of u times dx, so that's going to just be 1 dx. And so now up here we have this extra 2, which we can just pull that out to the front because that's a constant. And then our du is replacing our dx. Okay, so now when we go and make our substitution, we have 2 times the integral of 1 over u times du. And now we can go ahead and apply our integral rule for this. So this is just going to be 2 times the natural log of absolute value of u plus c. And then replacing our u function, we get 2 times natural log. In place of u, we're going to put in x plus 2. Okay, so pretty easy. Again, basically you just want to take your integrand, and once you've gone through and you go through your process, try to see if you can use general power rule, do your other techniques that you know of before. But the hint or the dead giveaway here is the fact that you do have a fraction. So a lot of times when you have a fraction as your integrand, try doing the u substitution with the u being the bottom function and see if it'll fit the natural log pattern. Okay, so here we have example 2, and again we have another fraction for our integrand, and we notice we just have a constant in the numerator again, so that can just come out to the front. So left over we have 4 minus 3x, which we're going to let be our u function. So that means du is just going to be the derivative of that, so that'll be minus 3 and then times dx. Okay, so looking up at our original integrand for our du function, we don't have the negative 3x, but that's okay because we can multiply and divide by a negative 3. And so now we have negative 3 times dx as our du, and then we have just 1 over u for the other portion of our integrand. So now substituting in, we have the 5 that we pulled out to the front to begin with, so we have a negative 5 and then over 3, and then we have the integral of 1 over u du. Okay, now applying our anti-differentiation rule, we have negative 5/3, and the antiderivative of 1 over u is just natural log absolute value of u plus c. And now going ahead and substituting back in for our u function. Natural log, our u was 4 minus 3, or 4 minus 3x, and then a plus c. Okay, example 3. So at this time, this would be an excellent place for you to pause the video, work out example 3 on your own, and then hit play to check your answer. So now when we do our substitution, we have 1/5 times the integral of 1 over u times du. And now applying your anti-differentiation rule, we have 1/5 times natural log absolute value of u plus c. And substituting back in, we have 1/5 times natural log of the absolute value of 5x minus 2 and plus c. Okay, so example 4. Here we have the integral of sine of x over 1 plus cosine x. Okay, so kind of looking at this problem, it looks a little bit different from the previous. So kind of go through your normal process. We know that we cannot use general power rule. It does not look like there's any sort of substitution that we can do so that we can simplify this. So then you would look to see if there's like an inside function just for like a basic u substitution. And we don't really have that either. So now we say, okay, well, it's a rational function. So let's go ahead and see what happens if we take the denominator and we let that be our u. Okay, so if we let u be 1 plus cosine x, when we take the derivative, we get minus sine times dx. Okay, so it looks like that'll work out because we have 1 over u, and then we just need for our du, we need to have a minus sine times dx, which we have a positive, so all we need to do is multiply and divide by a negative. Okay, so now doing our substitution, we have the opposite of the integral of 1 over u du. And taking the antiderivative, that gives us minus natural log absolute value of u plus c. And then substituting back in for the u, we have minus natural log of the absolute value of 1 plus cosine plus c. Okay, example 5. Again, this one looks a little bit different than the previous example. So again, using your normal strategies, you look and we see we cannot do power rule, but we do notice that the degree of the numerator is bigger than the degree of the denominator. So in the past, our strategy here has been to divide the numerator term by the term here in the denominator. So we want to go ahead and try to divide everything in the numerator by an x and then rewrite. Okay, so when we do that, we get the integral of x squared divided by x, gives us x, and then we have minus 2 times x divided by x, so that's a negative 2, and then we have plus 1 over x. Okay, so now that you see your rewritten integrand, this is just a basic power rule problem, but then this 1 over x, the integral of 1 over x, is just natural log. Okay, so using power rule for the first two terms, we get x squared over 2 minus 2x, and now the integral of 1 over x is just natural log x. Alright, so example 6, again this one looks different than the ones that we've looked at before. Go through your process, you can't use power rule. Right now we're not so sure that we can rewrite, just at first inspection. Degree of the numerator and the denominator are the same, so if you were to try to do u substitution on the bottom, for example, to get it in the form of 1 over u, that doesn't quite work because your du isn't going to have the right degree. Alright, so what we want to do is we want to try to rewrite this, and the problem is that you have this x squared plus 1 in the denominator, but you also have this x squared term up in the numerator. Okay, so you have two choices here. One, you can long divide. Okay, so off to the side over here, we could do 8x squared plus 9x plus 8, and we can divide that by x squared plus 1. And Okay, so if we do that, now we have, this would be our new integrand, and we could do the integration from there because we know the integral for 8, and here we have 9x over x squared plus 1. We could just use u substitution and that'll all work out. Okay, if you prefer not to long divide, the other thing you can do is just notice that you can do some algebraic manipulations. Okay, so here the idea is that you want to try to get this x squared plus 1 to cancel out of the top. Alright, so if I just rearrange this stuff in the numerator, I have 8x squared. If I put the 8 with that, if I group these two terms together, I can factor out an x squared plus 1. Okay, so now in my numerator, if I factor out an 8 out of the first two terms, I have x squared plus 1. And then I still have a plus 9x. And that's divided by x squared plus 1. Okay, so now I basically have in the numerator, I have this term and I have this term. Okay, so if I divide term by term, I'm going to get 8 times the quantity x squared plus 1 divided by the quantity x squared plus 1. So that is just 8. And then I have plus my second term in my numerator, 9x, divided by x squared plus 1. Okay, so there, I need to extend this page here. Notice what we get here, we get exactly what we got when we did long division. Okay, so this is just a matter of preference. If you prefer to long divide, if you really love long division, go ahead and do this. If you're good at just kind of noticing that you can just do that algebraic manipulation, then you can just do as I did. Alright, so now we can go ahead and integrate. So for our first term, that's going to be easy, right? That's just the integral of 8, so that's going to give us an 8x. The second term, we have 9x over x squared plus 1. It is a fraction. The degree of the denominator is larger than the degree of the numerator, so that tells us perhaps u substitution would be a fit here. So if we let u equal x squared plus 1, our du will equal 2x dx. Okay, we don't have a 2x dx, we have a 9x dx, but that's okay because this 9 will just pull out to the front of that integral, and we're going to multiply by 2, and then we're going to divide by 2. Okay, so I'm actually going to go ahead and split this up into two separate integrals so we don't mess up our balancing out here. So we have a 9 out in front, and then we have a over 2 out in front. Okay, so when I go to, I'm just going to rewrite this problem again so it's a little cleaner. So we have the integral of 8 times dx, and now we have 9 halves times the integral of 1 over u du. Okay, so go ahead and do your integrating, and we get 8x for the first one, plus 9 halves times the natural log of absolute value of u plus c. And then once you plug that back in, we get 8x plus 9 halves natural log absolute value of x squared plus 1 plus c. Okay, so that concludes just the basic anti-differentiation problems involving the natural log form. In class, we'll be looking at some other examples along with integrating some additional trig functions. So we'll see you then.